Okay, let's see what we've got going on over here. This is the original function right here, f of x, 11 plus 3 raised to the power the square root of x. And that's the graph of that function right there. Notice that the domain of that function is that x has to be greater than or equal to 0 because you cannot take the square root of a negative number. So as you map numbers in this domain to the range of that function, the smallest number that you can get for y is when x is 0. Because as x gets bigger than 0, this term right here is positive, and when we add it to 11, we'll get a bigger positive number. So when x is 0, 3 to the 0 is 1, 11 plus 1 is 12. That's why the domain is, or the range rather, is y has to be greater than or equal to 12. Now if we map elements of the range back to the domain using the inverse function, the range of the original function becomes the domain of the inverse. And as we map images in the range back to the domain, we'll get values for y that are greater than or equal to 0. That is the domain of the original function. So how do we find the original function? Well, or the inverse function, sorry. We interchange x and y. There we go. And then we want to isolate y. So we start by subtracting 11 from both sides, and we get 3 to the raised to the square root of y power equals x minus 11. To isolate this exponent, we have to take a logarithm of both sides. Now you could use log of any base that you wanted to. If you use base 3, the expression you end up with looks a little bit simpler. Over here, I've got what you would end up with if you use natural logarithms. But if we use log base 3, and then picture moving this exponent down front using the power properties of logarithms, the log of 3 base 3 is 1. So, and we take the log of both sides over here, base 3, and then we square both sides to get rid of that radical. So we have the log of x minus 11 base 3, the quantity squared. That's f inverse. Again, if you use natural logarithm, it would look like this over here, a little bit messier, but we still have to restrict the domain of the inverse function to be greater than or equal to 12. We can't have numbers in the domain that are different than that. Okay, in order to end up back where we started. Now, if I go to board 2, here's a picture of that both functions graphed on the same coordinate system. Here's the original function. This is f of x. This blue graph is the graph of f inverse of x. And you can see that I've plotted points and they're inverse points. So for the original function, when x is 0, y is 12. That means for the inverse function, when x is 12, y is 0. And if we know that a function and its inverse are mirror images of each other through the line y equals x. And if you actually connect these points, the line y equals x is actually the perpendicular bisector of the segment joining these points. So here, this is actually what's true. And I meant to mention, for a function to have an inverse, it has to pass the horizontal line test. So this red function here has to be 1-to-1 in order for it to have an inverse function, which means it has to pass the horizontal line test. An example of a function that does not pass the horizontal line test is y equals x squared. Does it have an inverse function? No, because it does not pass the horizontal line test. In other words, two different x's produce the same y value. So for example, if we had y equals x squared and we wanted the inverse function, we'd have to restrict the domain of this function to x greater than or equal to 0. That would give us just the right half of that parabola. And then the inverse function might look something like this. Okay, so there you go. Hope that helped. If you have any questions, post a comment.